in this video we'll be discussing about the quantum mechanical treatment of electron scattering. Consider there is a particle here and there is this incoming wave that is psi wave function is equal to e raised to I k r, and then the final wave psi f is equal to e raised to I k dash dot r. Okay, where the magnitude of k is nothing but the energy of the electrons. It is an elastic scattering. Only the direction changes, and the interaction is the interaction Hamiltonian is nothing but the Coulomb potential between the electron and the energy charge distribution. That is h prime is equal to integral minus e rho r d tau divided by 4 pi epsilon 0 r minus r prime. Okay, so where rho is nothing but the nuclear charge density and the integral is for the nucleus's full volume. Fine. The electron interacts with the entire nucleus and its energy comes from adding the effect of every tiny bit of the charge inside the nucleus. So that's the reason why we are taking h prime Hamiltonian, and then the probability of that is nothing but the square of the expectation psi I h prime psi f magnitude square. You will get the probability. So I'll write few statements. So this can be written in the integral form like this. Because this is bra, this becomes psi I. Okay, so ket is always the same, whereas bra will be the conjugate of it. Okay, fine. So there's this integral, then there is this h prime. This is a function of r, don't forget, and h prime psi f theta. Okay, the integral is entire volume, nucleus volume. Okay, entire nucleus volume. Now what you're going to do is just substitute. We know psi I is nothing but e raised to I k r, and then the conjugate is nothing but, so psi I star is nothing but e raised to minus I k r, and psi f the same thing. Okay, k dash of r. Fine. Now what you have to do is the multiplication of psi I dot psi f is nothing but e raised to I. I'll write it here. E raised to I r common. E raised to I r common k prime minus k. You just have to write it here. Okay. So these two terms become whatever I said right now, e raised to I k dash minus k r, and the rest of the Hamiltonian we have written here, this Hamiltonian. Okay, just you have to substitute it. You will get it like this. So this is integral sign is still there. E raised to I k prime minus k of r, k into r, into minus e rho r prime e tau prime divided by this is minus of e. Okay, minus e ka minus divided by 4 pi epsilon naught r minus r prime theta. Okay, so the problem here is that we don't know what exactly this term is. So in order to know that, we have to find the probability using inverse Fourier transform. So that is a only thing we can do in order to find this thing. So to find that, okay, so let's take this graph. So this is rho of p. We are only taking for the case of protons. So rho of p means charge distribution for protons versus r, and the unit is power minus 3 and femtometer. Okay, so there's this graph where this is for oxygen. I'll draw it like this. Okay, so this is for oxygen. This is for tin and this is for, okay, it should go flat and then go down, and then again for gold goes flat and then decreases. Same here, there's a flat and then goes. Okay, so this is 1608 oxygen, 118 tin, and 197 gold, right? Yes. So here we only take the graph for proton because electrons interact with proton and then scattering happens. That's the reason why we are only taking graph of proton in the beginning. Here the smooth decrease in the peak shows there's no sharp nuclear boundaries. So there is this smooth decrease. You can see there's a smooth decrease, and then the key observation is that the charge density is nearly constant near the center. See, the charge density is nearly constant and then decreases. So the decrease is smooth because there's no sharp nuclear boundary. So I'll write these points. Also, heavier nuclei will have larger radius and slightly lower central potential. So we can say that heavier nuclei, large radius, and lower central charge density. Okay, fine. Here, neutron distribution is not directly measured by the electron scattering. So we assume that neutrons are distributed similarly to protons, and in order to find the mass density, that is, we scale it by proton density, scale proton density by A by Z, where A is the total nucleons, which is the mass number, Z is in proton number. So we mass density scale the proton density by A by Z. Okay, so what happens is that oxygen will be 16 by 8, which is equal to 2, whereas tin and gold, the A by Z ratio is larger due to neutron excess. Okay, so after scaling, the mass density profiles for different nuclei nearly coincide, indicating a universal nucleon distribution shape. What I mean to say is that from the graph you'll understand. Okay, so this is how the graph looks like. This is for the whole charge, and this is R. This is for both protons and neutrons. So what I meant to say, like, after the scaling, the mass density for different nuclei nearly coincide. That means you see this portion, it's almost constant. The central density, that is a nuclear matter, behaves like a saturated liquid. So it's like universal. Whatever you take, the almost all the nuclear elements will have a constant central density, and the rest depends upon the outer side. Okay, so here the smooth decrease shows there's no sharp nuclear thing. So the downfall is the one which makes us understand if the nuclear boundary is sharp or not. So almost for every element, the central thing will be same, central density will be the same. The what defines the element is the nuclear boundary. Okay, yes. So how did we scale this from this? You just have to multiply by A by Z. So as a summary, I would like to say, graph typically means nuclear matter has a saturated interior design. Central region of almost all nuclei looks the same, and the nuclei having has a fairly sharp surface rather than fading gradually. And next, the point where the density drops to half its maximum value is used to define the nuclear age. So I'll take a graph. Okay, so it's like this. The point where the density drops to half its maximum value is defined as a maximum nuclear range. This distribution is mathematically modeled by Wood-Saxon function, that is rho is equal to rho naught divided by 1 plus exponential r minus r by a. This is for mass density distribution, where rho naught is the central density, r is the distance from the center falls to half its maximum, and a is the steepness, how fast it falls from highest value to the smallest value. Okay, now let me consider 2 points here. Let's say it's 0.9 rho naught, and here 0.1 rho naught, and the distance between this measures the steepness. Okay, how fast it falls from the highest value to the smallest value. Okay, so let's find out the value of r from here. You just have to use this formula. So rho is, we said, the first case is 90% decrease from the central density, that is 0.9 rho naught is equal to rho naught divided by 1 plus exponential r minus r by a. Bring this term there and then you'll get it as 1 plus exponential r minus r by a is equal to 1 by 0.9. r minus r by a is equal to ln 1 by 10, and r minus r is equal to minus 2.3a, and r is equal to r minus 2.3a. Okay, that's for 0.9 rho. Now I have to do the same for 10% decrease. 0.1 rho is equal to rho naught divided by 1 plus exponential r minus r by a. Do the same calculation. We'll get small r to be equal to r plus 2 by 3a, where a is approximately equal to 0.5 fm, irrespective of the size, shape, anything. A is always 0.5 femtometer, and r naught is 1.2 femtometer for light nucleuses. Rho naught, the density of the core, is 0.17 nucleons per fm cube. Okay, so from here we can understand this separation is almost 4.6 4.4 range. What this means is that there's this central density, as we said, is almost constant for all the nuclei, but then the boundary can be diffused, right? So the distance of the steepness from 0.9 to 0.1 is 4.4. So the distance from the actual nuclei to the actual nuclei, in the sense the central density to that of the diffused boundary, is 4.4 fm. Also, I forgot to mention we needed r, not r naught. So in order to find r is nothing but r naught a raised to 1 by 3, where a is the mass number. Okay, so using all these values you can find the small r value for 0.1% decrease as well as 0.9% decrease. Okay, so if you see that R and rho naught. These two are constant for almost all nuclei, but the deciding factor is R, this R. So if there's more nucleons, then R also increases. So this equation solely depends upon the capital R, where R's distance from center falls to half its maximum. Okay, so that's all for today. We'll see you in the next lecture.